Yeah. So rather than muting it, I just did call in. Okay. Yeah. Yeah. So this is basically due to the tunneling effect, which is basically a quantum mechanical effect that happens for the flow of current through the oxide. Okay. And again, there is one more type of leakage current that flows. That is primarily due to the PN junction diodes, because we know that a reverse biased PN junction will also have some sort of reverse saturation current. Okay, so due to that mechanism, there will be a kind of current flow between the source and the body, or between the drain and the body. Okay, so these are some of the leakage current, and today we'll focus more on the subthreshold conduction. Okay, and there are some set of problems that could come around this particular subthreshold conduction. We will do some set of problems as well. Okay, yeah. Now, let me begin with this topic. So as I said, subthreshold conduction is a kind of current flow that happens between the source and the drain, even for the value of VGS that is less than VT. Okay, so we call that non-zero current as the subthreshold conduction. Okay, so now we'll just look into like why this is happening, or how exactly we can model this particular current. Okay, so now what we do is that normally when we try to plot a graph of IDS versus VGS, what we assume is that the current is almost zero till I reach the value of VGS that is equal to VT. And after then, you assume that there is a kind of quadratic nature, and after a while, the device will enter into linear. So there will be some sort of straight line after this. Okay, yeah. So we will not worry much about this cara, which is above the value of VT. Okay. Now, in this case, we would see that the curve that I have drawn here is almost flat. Okay. So, but rather, if I try to change the scale of this particular axis, that is my y-axis, in terms of logarithmic, okay, with a base of 10, and when I try to replot this graph, we would see something different. Okay. Okay, so we would see some sort of characteristics, and this characteristics happens the moment the value of VGS is less than VT. Okay, so now when I have this kind of cara, which is being plotted against this logarithmic scale of this IDS, okay, so logarithmic scale would then be in terms of 10 to the power, I'm just choosing some random number, okay, so that the step size would be in terms of something in this particular scale. Okay, so every equal increment will be in terms of decade. Clear? So when I see this particular cara, you could see that there is a linear relation that exists between this logarithmic scale of IDS and the value of VGS that is less than the value of VT. Okay, so now the way to model this particular picture is we can use some sort of concept that we have studied in VJT. Okay, so first let me try to explain why this current flows and through what type of mechanism this current flows. Okay, and later we'll just try to model this part of the current that actually flows for the value of VGS that is less than VT. Clear? And again, I'm just taking this NMOS transistor. So clearly we could see that there is an N, which is basically the source terminal. Okay, and then there is a kind of P-type semiconductor, okay, which is basically the body. So there is an N-P-N transistor, right? So it can be visualized something like this, with some sort of a parasitic BJT transistor that is being formed just because of this PN junction diodes across the source and the body and across the drain and the body. Okay, so due to which there happens to be some sort of reverse bias, and we know that each of these PN junctions are basically reverse biased, and it is through this the current flows. Okay, and what type of current is that? It's basically a reverse saturation current. Okay, now let us try to model this particular current. Okay, so I'm not going to explain how exactly these currents are being written down, but I'll just give the final expression. Okay, so the current that is flowing for the value of VGS that is less than VT could be modeled with some sort of expression. Okay, so now the way that this particular plot shows a kind of linear characteristics between the logarithmic scale of IDS versus a linear scale of VGS, one could see that there is a kind of relation. Okay, so now can anyone tell me like what type of relation that the IDS and VGS defines in this particular zone, where we are trying to plot against the logarithmic scale of 10?
Linear.
No, it cannot be linear, right? Because yeah, it's actually linear. So which means that I have something like logarithmic scale, and this is my y-axis. So y equals to mx. So there can be some sort of slope value here.
Exponential.
Yeah, that is what I wanted. Okay, so now that in order to remove this logarithmic scale, I have to take anti-log, which is nothing but the exponential on both the sides. When I do this, then what happens is that you would end up having something like exponential term. Okay, so this is what we would end up. So even our case, the current equation that I'm about to write will also have this kind of exponential relation with respect to the value of VGS. Okay, so there is a reverse saturation current, which I'm writing it as just IS. Okay, sometimes it can also be written as IDS naught. Okay, so we will not worry about what notation to be used. Okay, in general, there is some sort of reverse saturation current, and that current has to be multiplied with some sort of.
Excuse me, sir.
Yeah.
The log is taken base 10 over there. So how can it be exponential? E.
Supposed to be ln.
Yes, if it's ln, it will be exponential. Then E will come.
So it's supposed to be ln, right? Okay, then I think it's fine. Yeah. Yeah, it's supposed to be some sort of logarithmic scale, and they actually gets related with an exponential term. Okay, and again, this is a concept basically through this BJT structure that we are trying to derive. Okay, yeah. So here we have some sort of term through which we could able to relate the value of VGS. Okay, and also there is also one more term that happens over because of the PN junction, that happens because of the drain to source, or basically because of the drain and source. We also have some sort of current flow because we need some sort of potential difference between the drain and the source in order to make the current to flow, right? So we need some sort of component that is relating to our VDS. Okay, so again, this is there is no proof that I can give for this. It's just the equation that I'm just writing it down. And right now, if at all, if the value of this VDS, okay, if the value of this VDS is much greater than the thermal voltage, which is nothing but KT by Q. Okay, maybe I could write it as VK. Okay, so that we will use this VT for representing the threshold voltage and VK for representing the thermal voltage. Okay, so if this expression is satisfied, then obviously what happens is that the e to the power most negative term would end up having a value of 0. Okay, so in that case, one could approximate this current flow of IDS to be equal to IS into e to the power of VGS minus VT divided by n times that of VK. Okay, so I've just reduced this expression of KT by Q as just VK, and then I've substituted that notation over here. Okay, yeah, so this is the current flow, and now one could also wanted something out of this device, right? So when I try to plot this particular curve, we will try to evaluate the slope factor. Okay, so I want to evaluate the slope factor with something known as S, and I'll try to define the slope factor. We want to switch to the very lowest current at the earliest. Okay, so I want the slope to be much steeper. Okay, I want to decrease at a much faster rate. Okay, so this is what we want to evaluate through this slope factor. The rate at which I'm trying to switch off is supposed to be much faster. Okay, so that can be read by the slope factor.
Excuse me, sir, can you repeat it? I couldn't follow what you explained.
Yeah. So I'm talking about the slope factor. So this slope factor is an important quantity. In order to know whether our device can quickly turn off to a very small amount of current. The moment I switch the value of VGS below the value of VT, I want this current to go to a very low values. So we basically want to measure the slope factor of this in order to measure how fast the current is getting reduced for the value of VGS that is below the value of VT. Okay, so that is the measure that we are doing in terms of slope factor. Okay, so let me try to define more formally rather than speaking it out. So I'm just going to define a factor which is known as slope factor, yes, which basically measures the inverse rate, okay, of decline of IDS with respect to VGS below the value of VT. Okay, so it actually measures the quality of the technology or of the MOSFET that we are using. Okay, So now the way that we are going to measure this particular slope factor is by reading out the slope value of this. Okay, so now what I'm going to do is that I'm just going to take two different currents, okay, and then the corresponding VGS values. Okay, say for example, I'm just picking one of the current at which my IDS 1 is equal to 10 to the power minus 7, okay, and the corresponding value of VGS, let me take it as VGS 1, okay, and let me take the second one, which is the IDS 2, where the current ID2 supposed to be a decade away from this value of IDS 1. Clear? So clearly there is a difference of 10 between both these currents, and I choose that corresponding value of VGS as VGS 2. Clear? So you got the differences, right? So now that I just want to measure the slope factor, I make use of this equation that I have written down earlier, that I have IDS 1, which is basically equal to 10 to the power minus 7, okay, amperes, and that is related to the value of VGS as VGS 1 minus VT divided by N times that of kV. Now I have one more current which I have taken, which is a decade away from this IDS 1. Okay, the IDS 2, the difference between the IDS 1 and IDS 2 is supposed to be 10. Okay, and that can be returned in terms of the same expression, but in the place of VGS, I am just picking as VGS 2. Okay, the corresponding value of VGS 2. So now what I can do is that I divide both these equations. Okay, 1 divided by 2. Then I would end up having something like I will take ln on both the sides, okay, so that this delta VGS is what I'm going to define as the slope factor, which can be written as, so I'm just going to expand this, which is KT by Q in the place of VK, and then into ln of 10. And the unit for this would be like millivolt per decade. So hope that you're clear with the slope factor here. So the slope factor is something that we are trying to measure for the current that flows below the value of VGS that is less than the value of VT. Okay, and how are we measuring is that we are taking two currents that are a decade of difference between them. Clear? So I've just chosen here 10 to the power minus 7 as one of the current, and the other current that I'm taken is 10 to the power minus 8. Okay, so I've taken that difference and the corresponding VGS values I've taken, and then when I try to measure, their difference is supposed to be equal to this. Okay, so now clearly for room temperature, okay, that is for a temperature of 300 Kelvin. Okay, one could write this VK or this KT by Q could be approximately equal to sometimes 25 millivolt, or sometimes they used to write 26 millivolt. Okay, so what we do is that we'll just fix this 26 millivolt as our quantity here. Okay, and in case if the value of N is equal to 1, then I just want you to compute what is the slope factor of that. Okay, so this is just a kind of ideal case where having an N that is equal to 1 is pretty much rare. Okay, so I just want you to compute and get me the value of the slope factor for N that is equal to 1, so that you can just directly substitute here, and you have to have your calculator in order to compute the remaining part. Okay, so the value would be closer to 60 millivolt per decade. Okay, yeah, so exactly if you want, it is like 59.86, but we would approximate that to be closer to 60 millivolt per decade. Now, what does this tells us? Okay, and this is the most important thing. Now, this tells me that in order to reduce the current from 10 to the power minus 7 to 10 to the power minus 8, I need only 60 millivolt difference between the VGS. Okay, so this is actually a better quantity, but let us take N that is equal to 1.5, which is normally found in the MOS technologies. Okay, so when I have the N that is equal to 1.5, the slope factor becomes something like 90 millivolt per decade. Now, what does this mean? Which number is good? having S that is equal to 60 millivolt is good, or having S that is equal to 90 millivolt per decade is good? So which one among you?
90.
90.
Okay. You see, in order to reduce from 10 to the power minus 7 to 10 to the power minus 8, I have to have the difference. The VGS1 has to change to VGS2 so that the VGS2 can be returned as VGS1 plus 90 millivolt. So I need a 90 millivolt to reduce this current. Whereas here, when I have N that is equal to 1, okay, so let's say, for example, I have VGS1 here, and I could write this VGS2 as VGS1 plus just 60 millivolt. So which one is good in this case? Which is stepping down much faster?
N equal to 1.
Yeah, N equals to 1, because I need only 60 millivolt to reduce the current from 10 to the power minus 7 to 10 to the power minus 8. Okay, so this is actually better option than compared to this one. Okay, so maybe the way that I have marked here as a slope factor might confuse you. The only thing that I wanted here is that through the slope factor, we are trying to evaluate this quantity. Okay, so how much of the VGS that I needed in order to reduce the current a decade below. Okay, so the rate at which I want to reduce is what we are trying to compute through this slope factor S, okay, or the differences in the value of VGS. Okay, if I could able to make this VGS1 and VGS2 as close as possible, then the rate at which this would decline would be much faster. Okay, so for this new graph that I've drawn, you could see that I need only a small amount of VGS to reduce from 10 to the power minus 7 to 10 to the minus 8. Okay, so in that case, the S factor will be much smaller. Okay, so I need S to be small, or basically the delta VGS to be small in order to reduce the current by a decade. Okay, hope that it makes sense. So we want this delta VGS to be as small as possible. Okay, so in this case, having an N factor that is equal to 1 will give us the minimum VGS to reduce the current by a decade. Okay, yeah. So now let us do a simple problem here. Yeah, hope that you could be able to see this particular problem. So what is the minimum threshold voltage for which the leakage current through the off transistor, that is when VGS is equal to 0, is 10 to the power 3 times lesser than the transistor that is barely on when VGS is equal to VT. Okay, so assume that the value of N is equal to 1.5. Okay, so we would be solving two things. Okay, one with N that is equal to 1.5, the other one with N that is equal to 1.3. Okay, so SOI stands for silicon on insulator, which is again a kind of technology through which MOS transistors can be fabricated. Okay, so we'll talk about these things later on when we discuss about this unit number 5. Okay, so as of now, we'll just won't worry about this SOI or any other factor. Okay, we'll worry about only the factor of N. So now, given this question, how would we actually start? So we actually wanted you to calculate the threshold voltage of the device based on the given data. We know that the current, there is some sort of current, okay, at these 2 points. One, when the value of VGS is at VT, there is some current, which is IDS1, let us take, and there is also one more current, okay, which is IDS2, when VGS is equal to 0, okay. So, and the difference between these two are 10 to the power 3, okay. That is IDS1 is 10 to the power 3 times greater than the value of IDS2, okay. That is what is being given here. Now, we want you to compute the value of VT based on this expression. So how I can rewrite this currents when the value of VGS is equal or less than the value of VT? How I can replace this IDS1 and IDS2 expressions? And we also have to assume that the value of VDS is much larger than the thermal voltage. Okay, so this is an assumption, so we can leave out the exponential part that was there in the original expression. Okay, yeah.
Sir, we can use IS into e to the power something formula, no, sir?
Yes. Yeah, this is what we wanted actually. So in this case, we know that in general, I can bring out the expression of IDS. Okay, so which is defined as IS e to the power VGS minus VT divided by N times that of VK. Okay, so I can use this equation and I can write it as IS e to the power, and the value of VGS that I have when I am at VT will become 0, right? So VGS,
Zero.
yeah. So what happens to the exponential of 0?
1.
It will be 1, okay? Yeah, so it is something like IS into 1, okay? And on the other hand, I have again IS e to the power, and what is the value of VGS that I have here? That is equal to 0, right?
0.
Yeah, so I have something like minus VT divided by n times that of VK. Okay, so I could cancel out these two terms, and I could bring the exponential on the other side, Vk, and I have this 10 to the power 3, and take ln on both the sides so that we can get rid of this. Yeah, so through this formula, I could find the value of the threshold voltage of the transistor. Okay, so you can use this Vk to be approximately 26 millivolt, okay, at the room temperature, and you just get me the value of this.
So 269 milli.
Yeah. So approximately it comes around, yeah, closer to this 269.4. Approximately, I can write it as 270 millivolt. Okay, and that is the threshold voltage of this particular transistor. Okay. So now there is one more part of this. Okay, if at all, if I'm using this SOI, which has a smaller value of n, what is the threshold voltage that is required for SOI if n is equal to 1.3? Okay, so now this time what I do is that I know that I could rewrite this expression on the other way. Okay, so which is nothing but Vt can be written as n times Vk, and there is a ln to the 10 to the power 3, right? So this 3 can be brought it in front, and I can write it as ln of 10 itself, right? So now this particular quantity that I have here is a well-known factor, which is nothing but the S. Okay, and just by multiplying by a factor of 3 would get me the threshold voltage of the device. Okay, so now in case if I know this S factor, so now for SOI, we know that the N is said to be 1.3. Okay, so based on this quantity, first let us try to calculate the slope factor, and then we know that this slope factor has to be multiplied by a factor of 3 in order to get the value of the threshold voltage of the transistor, right? So I can use this way as well. Okay, so this is one more way by which we can find the threshold voltage. Okay, or you can use the same expression. The only thing is replace this n with a factor of 1.3. That is also fine. Okay, so sometimes given an S factor, we can directly do this as well. Clear? So this is the slope factor that I have, and once I know the slope factor, what I can do is that I can just multiply by a factor of 3 to get. Okay, yeah. So now what I'm going to do is that I'm just going to run in a much faster phase. Okay, so the second type of leakage that we have is about the gate leakage, and as I said, this leakage happens just because the thickness of the oxide for lower technologies has been dropped to a thickness which is almost like 15 to 20 angstrom, so which is like 10 to the power minus 10 meters. Okay, and due to which what happens is that there is some phenomena which is known as tunneling that happens, and that results in this gate leakage current. Okay, and again, this gate tunneling can be classified physically into two kind of physical mechanisms. One is like FN tunneling, okay, which is more important when we have a moderate thickness. Basically, this kind of tunneling is used for programming the EE probe. Okay, so apart from this, we will not discuss much about this gate leakage things. And there is also a direct tunneling, and this direct tunneling happens even at low voltages with very thin oxide. And this is the most dominant leakage component that we have for the lower technologies. Okay, so the direct tunneling is one of the dominant factor when you go for lower technologies. That's it. We will not go much in depth. And the final type of junction leakage that we have is about the PN junction. Okay, so here I have a structure which is known as N-well structure. We will talk about this N-well, P-well, and there is something known as twin tub and many such factors when we discuss about unit number 5. Okay, so as of now, you assume that an N-well is something where we will have this PMOS transistor, and the P substrate is where we will have this NMOS transistors. Clear? So as you could be able to see that there is a PN junction, okay, across the source and the body. And even in the case of a PMOS transistor, there is some sort of PN junction diodes. Okay. Now we know that normally these p-n junction diodes are in general reverse bias. So in this case, you could see that there is a p substrate. So this p substrate is connected to the ground through this p plus region. Okay, so it is something like we are trying to fix some sort of body potential, which is generally a ground for an NMOS transistor. So similarly, I would be having an N well. This N well is completely biased to a VDD. Okay, so to some power supply. Clear? So there is some sort of reverse bias between this PN junction due to these kind of body that is being connected to a fixed potential. Okay, whereas the source and the drain may or may not have the same potential as we have for the body. Okay, so they may have a higher potential than compared to this. In the case of an N-type semiconductor, whereas in the case of a P-type semiconductor, these P plus regions normally will take voltages which are either equal to VDD or sometimes lower than the value of VDD. Clear? So right now, you might not be able to appreciate this particular phenomenon just because we still have to go a long way. Okay, so the only thing is that these PN junction diodes are in general, they are reverse biased. Okay, and whenever there is a reverse biased PN junction, we know that there is some sort of leakage current, and one could model that reverse biased leakage current through this kind of expression. Okay, so here in this case,
Sir,
yeah.
sir, why is there P plus and N plus in P substrate? Sir, what is the use? So why will we?
This one, this
Yes,
one.
sir.
Okay,
Sir.
because this is for the source and this is for the drain. These N plus regions that are there in our P substrate is by construction, we will have this kind of structure.
I'm talking about P plus and P minus substrate, sir. What does it
Here,
exactly?
this one you're talking, this
Yes,
P
sir.
plus. Okay, yeah. So this is something like we are heavily doped this P-type material just because in order to reduce the resistivity, because even the resistance of the material will also matters when we try to apply some sort of potential. Say, for example, if I have a very large resistance, the voltage that I'm applying here, 5 volt, will be dropped very heavily when the resistance is large. Okay, so we want to reduce the resistance so that I could at least produce something like 4.9 volt if the value of resistance is small. Okay, but in case if the resistance is large, okay, then when I apply a 5 volt, then at this point I would get something like 4.8 or 4.7 volt, something like that. Okay, so we want to reduce that resistance when we try to apply some sort of potentials here. Okay, so due to which we generally go for heavy doped materials here. That's the reason why we have this P plus regions here, and over here there is an N plus regions, so which is basically meant to bias this body of both the PMOS as well as the NMOS. Does it make sense?
Sir, okay. I didn't understand properly, sir, because he said that for increasing the voltage we use the P plus and N plus, sir. Sir, but how that helps in this format? I didn't get that.
No. You see, the entire body is supposed to have some sort of potential, some sort of voltage. Okay. So now I'm applying a voltage through this particular ground. Okay. And that voltage has to be supplied through this entire structure. Okay. But the opening that I'm giving here is it's something like how I can say. Okay. So every material that we use has some sort of resistance. Okay. So say, for example, when I'm trying to apply some 5 volt, even when you take a metal, okay, a lengthy wire, which runs like kilometers away. So this 230 volt that you apply in one end, when you reach to the other end, it will be like 220 volt. Okay, so basically there is some sort of resistances that is along the path. Okay, and in order to reduce the resistance, we use this aluminum wires. The reason why we are going for aluminum wire is that the resistance of those wires are a bit less. Okay, so even here, I'm trying to apply this potential because it's a planar structure. Like I have to talk more about the semiconductor over here, but these things has to be discussed during our unit number 5. So planar fabrication is something like all our terminals will be at the top level. So we will have a general substrate or something like a P substrate. Okay, and then what I do is that I try to dope things like a P plus material with some sort of masking, and then later there will be a metallization. Okay, and then I will have a wire, and through the wire I would be connected to an external power supply like a 5 volt supply. Okay, so what happens is that these voltages the current flows through this shorter wire will have a much larger resistance. And again, when I'm entering into the substrate, I need a low resistance path. Okay, so what we are trying to really do here is that we want to reduce this voltage that is getting dropped here. We want to observe whatever the voltage that I have here onto this entire surface as uniform as possible. It is something like to reduce the resistance, not much physics behind this particular P plus region. Okay.
Done, sir. Done, sir.
Yeah. Sorry if I couldn't able to explain properly. Yeah. So, but these structures will not actually create any sort of PN junction. It's only the opposite structure, like N plus with P-type semiconductor will create a PN junction. And even here, an N well, which is nothing but an N substrate for a PMOS, will create a PN junction with the P plus sources and the drain structures. Okay, so those PN junctions are normally reverse biased, and they generally conduct some small current across them. Okay, even the N well that I have drawn here also creates some sort of PN junction between the P-type substrate and this N well. Okay, so you have almost like too many parasitic diodes throughout the entire structure. Okay, and all of these structures work in the reverse bias conditions, and due to which there will be obviously current flow through them. Okay, and we call that as a junction leakage current. Yeah, which is the current doesn't serve for any purpose; it just goes waste. Okay, and one could model the current through this kind of equation where the diode voltage VD can be written as minus VSB between the source and the body, or VDB between the drain and the body. Okay. Yeah. So nothing much apart from these discussions with respect to the leakage current. So today we discussed about three types of leakages. One is the subthreshold conduction. The second one is the gate leakage. So the most dominant is the direct tunneling impact. Okay, so due to this tunneling effect, the gate leakage current flows, okay, between the gate and the body. And the third one is the junction leakage. So these are the three important leakage current components that we have. Okay, so the next couple of things as well, I'll just run very fast. Okay, so there's nothing much to discuss. The only thing that we are going to discuss is that there are certain parameters that varies with respect to the temperature. Okay, so namely the mobility. Okay, so the mobility of the carriers, charge carriers, generally decreases with the rise in temperature. Okay, and due to this, what happens is that the saturation velocity also tries to get reduced with respect to the temperature. Now, the reason why this mobility getting reduced with respect to temperature is that the lattice structure actually starts vibrating when you raise the temperature of the material. Okay, and due to which the carrier will be get hit by these vibrated phonons, and due to which the mobility of those carriers will get reduced. Okay, so once it gets reduced, saturation velocity also gets reduced, and the other components like the threshold voltage of the device also decreases linearly with the rise in temperature. Okay, and here again the on current, okay, also decreases with the rise in temperature, and the subthreshold conduction, which is the current which we don't want to exist, rises exponentially with temperature. Okay, so you see everything happens in the opposite direction. We want higher mobility just to make the switch on and off very fast. Okay, and we want this threshold voltage of the transistor to be much higher so that we can set some sort of switching voltages. Okay, that again gets reduced, and we don't want the subthreshold conduction current to exist at all. But unfortunately, when the temperature rises, it increases exponentially. And whereas the one good thing is that the gate leakage, okay, there is something which is independent of the temperature because of the tunneling effect. Okay, so these are the side effects that we have, and there are some couple of graphs, not too many, okay, which shows the temperature variation with respect to the current. Okay, so what happens the moment you have the increase in temperature, how does the graph shifts, okay, is what has been given. Okay, so clearly the graph that has been plotted as ID versus VGS was plotted against the square root of IDS. Okay, so this is the case when we have saturation current. Okay, so we know that the saturation current is actually written as VGS minus VT the whole square. Okay, so in order to show the linear relation, we have taken a square root on both the sides. Okay, and that's the reason why you would see the VGS was being plotted against the square root of IDS here, and that shows some sort of linear relation between the temperature VGS and the square root of IDS. Okay, so you could see that at high values of VGS, the current has a negative temperature coefficient. So what does it mean is that the rise in temperature actually reduces the current, okay, at high values of VGS. But for low values of VGS in this particular region, we have a positive temperature coefficient. So when I say positive temperature coefficient, this means that a rise in temperature actually raises the current, okay? So we will have a high current when we have a positive temperature coefficient when the temperature rises, okay? So that's it. And with this, let me stop here.